Hey guys, welcome to the second part of training our first neural network. Today we'll be going through backpropagation as well as keeping track of metrics like the cross-entropy loss and network accuracy. Without further ado, let's get on with it. Okay, cool. Now that we've completed the forward pass, we're going to actually have to do the backward pass, but one more thing is we're going to actually have to compute the loss. And so the loss that we're going to use is we're going to use the cross-entropy loss. This loss is just given by this equation over here. It's the loss that they usually use for multi-class classification. And it's also known as the negative log likelihood. So you can see the negative comes from here, and then we take the log of the probability, which is the predicted probability, and this is the true probability. And we do this for all the classes actually. So we sum it for all the classes. But if you notice that this is the true probability, and in our case we'll only have one class that has 100% probability, and then the rest will have 0. So that means all of the logs will be times by 0 for every single class except for the class that is the true class for that example. So we actually just need to compute it for the true class, which is what we're going to do now. So let's just do that. So the loss is equal to negative log. So we have the negative log. And then because it was times by 1, we don't actually have to add that to the front of, so instead, x, and then we're going to take all the values from the x, which is, I think there's only 1, so we can actually put 0 there as well if we want. And then we'll take the label of this, the index at the label, which is the true label. So take that, and then after that is computed, we'll actually just take the mean. Okay. So after we've computed the loss, we'll do loss dot backward, and so we've left out a crucial step here in the backward pass. So the bug in our code is that when you call the loss dot backwards, it appends to the gradients that are already that have been computed for the weights. So what we got to do is actually we have to set these gradients to 0 before we do the backward and compute the gradients again. So let's just do that quick. We can actually just, instead of setting them to w gradient or w grad is equal to none, instead of setting them to 0, we're going to set them to none, and this gives us the same effect. So it should be b1, and this is b2. Then this is equal to none. Cool. And then once we have that, we'll actually have our loss, and then we'll just say, okay, gonna add to our running. We'll just say actually loss is equal to loss.item, and then let's just print the loss. And let's see how it is. Let's actually do it for every 100th step, because it's logging a bit too much. So let's just do if step is equal to 100 is equal to 0, then we're gonna print this. Cool. Let's just run that. Okay, but it's really hard to tell because if the network is making any progress, because each individual example might have a loss greater than or less than the previous example, because it's all independent examples with different pixels in different areas. So let's actually just we're gonna use this running loss to compute that. So let's just do that quick. So first off, we're gonna do running. We're just gonna say running loss actually is equal to, so is equal to that, and then I'm gonna say running loss. I'm gonna print this, And actually, let's divide this by 1000, and we're going to want to put this to +1 instead, so that it doesn't print the first example. Cool. So once we have that, we're going to print, and we're going to set the running loss to 0 again, so we can restart the cycle of computing the loss. Okay, you can see that doesn't seem to get any better. Why is it not doing this? Oh, that's because we forgot to update the gradients. Yeah, so we need to update the data with the gradient. So minus equals w1.grad times lr, which is the learning rate. Set to 1e to 5, then w or b1 is equal to data equals minus equals w or b1.grad times lr. Then we'll just do the same for the other thing as well. Okay, so let's just actually do it this time. Okay, what's going? So I managed to find the bug in the code. It wasn't really a bug, but I changed the learning rate from 1e to the -5 to 1e well, to the -3 instead. So basically what the learning rate does is it changes whether the network learns faster or slower, and depending on the loss curve is how you'll choose this learning rate. So if you choose too big of a learning rate, you're not going to be able to get to like the minimum of the loss curve, because it'll be bouncing around on the loss curve. And if you choose too small of a learning rate, it's going to converge to the minimum a lot slower. So it's important. The learning rate is important to pick. So now that this actually works, you can see that loss is getting lower. So now that we're tracking our loss, we actually want to track also the number of correct that we're getting. So let's just let's do that. So to get the number of correct predictions, we're gonna take the output of the network, which is this x over here, and we're gonna find the highest probability out of the numbers that come out of there, out of the probabilities that come out there. So let's just do that quick. We're going to use the torch argmax to find that. So let's just do it above here. So torch arg max of the network output, which is this. Then we'll get that, and after that we'll actually check if it's equal to the label. If it is, then we're going to say running correct plus equals 1. So we got 1 correct. Then after that we'll just add this over here to, so running correct and divided by 1000, because we're doing 1000 examples. Just zoomed in by mistake there. Once we have that, we can, oh yes, we also need to change the running correct to, well, then let's just add in, so loss equal to that, and then running correct is equal to, let's just make this accuracy. So this would be the number of correct, the number of correct over the number of predictions, which would be 1000 for each one of these steps. So let's just run that and see. We're gonna get not too good of a predictions, but I think we did something wrong. Yeah. So if you didn't spot the error in this code, it's that we're doing it for every 100 steps, we're dividing by 1000. That's why the loss and the accuracy is off. So let's just run that again. then you can see that it's actually at 90% already. But let's actually just reinitialize. So we're setting this all to the random values again, and then we're gonna run this. And let's see it increase. So you can see it's getting up to already pretty high, 68. Then it's 70 mark. And then it's up to 80 already. And you can see, yeah, it's bouncing around there. So if we actually adjust the learning rate here, so let's just try not to run this again. Let's adjust it to 1/8 to the 5, see if we can get a better learning rate. So this is, or a better accuracy with a smaller learning rate. Yeah, we can see we're heading up to 90, but it's still kind of bouncing around a bit. So I hope you guys enjoyed this tutorial on how to train neural networks using PyTorch. We're not actually using any of the inbuilt layers for of PyTorch. Instead, we're using the tensors natively, which is kind of cool. So you guys know how it works, the inner workings. But after this, we'll actually just be moving on to using these modules and the layers that are in PyTorch to make it a lot easier for initializing instead of just doing the tensors by themselves. But it's a good kind of, it's good to have like a base understanding of what's happening under the hood. But yeah, I hope you guys enjoyed. I hope this was very helpful. Please leave a like and subscribe, and I'll see you guys in the next tutorial.